Welcome back. And what do we have here? We have to do this analysis on our test. There'll be a whole page of these. And we always start by analyzing the carbon with the leaving group. So, I'll do that in green. R with leaving group. Okay. I was looking for an easy way out. Didn't find it. And my computer doesn't like me. Here we go. Rx with the leaving group. Top example, it is primary. And I need to see your conclusion. So I don't need sentences up here. I need you to tell me what you're analyzing, what category it's in, and what's your conclusion. Remember, a primary carbon cannot make a carbocation, so SN1 is not an option. That gives you what the option is. A secondary carbon can make carbocations reluctantly, or it can have their backside attacked somewhat reluctantly. We don't know if it's going to be SN1 or 2, and I want you to reflect that you don't know that by writing SN1 or 2, I don't know. My students have taught me the expression that I do like a lot, and then they just say, Mabarif. I don't know. Okay, so that's good. That's a conclusion. It's worth a point. Then we always analyze the nucleophile. I think in previous semesters, nucleophiles have been blue. Blue, new. New. Do you remember the 3 categories of nucleophiles? I will remind you, they are strong. All of them are anions except the carboxylates. They are moderate. Neutral nitrogen, neutral sulfur, or carboxylates. Those are moderate. Or they are poor. Neutral oxygens. This is RS minus, ethyl S minus. That's strong. And the same category down below. Strong. Which reaction has the nucleophile in the rate determining step? And only SN2 involves the nucleophile in the rate determining step. So strong nucleophiles favor SN2. And there you go. So once again, it looks like there's not a lot of writing here, but there are 3 things here. What are you analyzing? You're telling me I'm analyzing the nucleophile. What category is it in? Strong, moderate, or poor? Strong here. Strong always favors SN2. So conclusion is the 3rd piece. Then the solvent, there's 3 pieces there. 1, tell me you're analyzing solvent. Do it 3rd. Top one is ROH. Can I remind you the 3 categories of solvent real quickly? Polar protic solvents are capable of hydrogen bonding because they have H bonded to O or H bonded to N in their structure. That's this category. Polar aprotic solvents, you've just got to learn the 4 I gave you. There are hundreds, but learn the 4 I gave you. Acetone, which had a carbon ketone, acetonitrile, which had the C triple bond to N, dimethyl sulfoxide, which had this S double bonded to O, and dimethylformamide. None of those are here. We have the polar protic here. Polar protic. And that one was the one that stabilized carbocations, and that's going to help your SN1. And down here, this is a nonpolar solvent. Give me its category. Nonpolar solvents slow down SN1, so what's going to take over? SN2. Now your conclusion up here. If you write SN1 here, you're trying to tell me that you can make a primary carbon become a carbocation. That does not happen in this universe. You could have written SN2 in this box immediately. If you did so, please do not stop your analysis. This is a 4-point box. You get a point for green, a point for blue, and a point for red, and a point for the correct conclusion. It's 4 points. That's not trivial. Okay, down here, I didn't know, so I can't use that to make my mind up, but the other two things said SN2. So I'm basing my decision on the red and the blue. So half of it in blue, half of it in red. I know this sometimes drives you guys crazy. Just write SN2 and you get your point. They're both SN2. Cool. What happens in an SN2? This page does not require a mechanism, but I'm going to give you one for free just because we're learning these for the first time. And potassium or sodium is a spectator. It's just balancing the minus. So it's this one. And both of these are SN2. So you're coming in with a backside attack on a carbon with a leaving group. Get some good practice here. Backside attack. Carbon with a leaving group. I don't need to see the leaving groups. If you want to put them somewhere, it's fine, but you don't get points for them. Put them outside the box. BR minus for both of them. You get points for showing me what happens to your carbon. So we have a 4-carbon chain in Rx. 1, 2, 3, 4, 5. Sorry, I miscounted. 2, 3, 4, 5. And now it has a sulfur bonded to it. Sulfur that's blue and has an ethyl on it. This sulfur has just a methyl on it. Makes a new bond to a carbon. And hey, if you're worried about stereocenter, here's what you do. 1, 2, 3, 4. You got to remember this thing started S and it better end R. So one way to make that R is to put the H on a wedge and make that new bond a dash. All the way, please. And yeah, R is now S. And that's, oh, S is now R, sorry. Used to be S. I don't know which colors, I don't want to mislead you. Used to be S. Now it's not S, therefore it's R. And that's the end of those two. Let's see what happens in problems 3 and 4, shall we? There's no next page. I thought I had these ready for you. 5 of 6. Well, this is a blank page, isn't it? Let's fix that now before I forget. I know they're annoying. Okay, there's page 5, the righteous page 5. Doing problems 3 and 4. And we need a little room for notes under 3 here. Same analysis. Let's see. We did Rx first. No, we did it in green. Then we did nucleophile, blue new. And solvent last. Please do it in this order. There's a method to this madness. Rx is secondary in the first one. It's the same molecules we saw before. Your conclusion for secondary is always SN1, 2. I don't know. Your nucleophiles ROH. And that is a neutral oxygen. Those are poor. Poor. They favor SN1. by slowing down the SN2. Solvent. You say, wait, there's no solvent. Ladies and gentlemen, there's always solvent. We don't do gas phase reactions in this course, although there's people that devote their whole lives to studying gas phase reactions. From a practical sense, we don't do those reactions. Solvent, when it looks like it's missing, what do we do? Some of you already know. When it appears the solvent is missing, then the nucleophile is also the solvent. And the reaction is called. It's very common. Remember, when you do a substitution reaction, you're breaking off a piece and replacing it with another, right? So that's a form of lysing, cutting. So the solvent is doing that cutting. So we call it Solvolysis. Good name, huh? I like good names, you know that. And that's got to be red. Talking solvent. Okay, so solvent, ROH, in red. Please don't tell me it's a poor solvent. There is no such thing as a poor solvent. All solvents are good. Okay. Your three categories were polar aprotic, polar protic, that's this one, and non-polar. Hydrogen bonders were polar protic. You better watch your spelling here. You leave this A off and you have the wrong category and the wrong conclusion and the grade you're not happy with. Oh, and I just wrote aprotic. It's protic. The A makes it protic. Wow, that's big. It's protic. H bonded to O is what makes it proton attached to O, not aprotic. Don't talk and write at the same time. It's hard when you're doing these videos. Okay, polar protic favors the reaction where there's cations because these things stabilize cations. So I got one thing saying I don't know, the first thing, and the other two saying SN1. Guess what your conclusion is? You got 2 out of 3. SN1, carbocation. See what I did there? Now you've got to show me what happens. Mechanisms not graded on this page, but when we're learning things, the mechanism should always be in the back of our mind. In an SN1 reaction, which you just told me this is going to be, this has to become a carbocation, right? So leaving group leaves, you get a cation. It's flat. Then the nucleophile does its thing. Lone pair attacks the carbon. Don't put the product in the box. We're leading up to the box. We're not in the box yet. And you get a 50-50 mix of R and S. How come? Because carbocations are flat. And this is not the final product. Please don't put strong acids as final products. What does strong mean? That's pKa is -2. It's an oxonium. Strong means it's going to react. What's it going to react with? The solvent. You want to show the mechanism for that? Why not? Solvent, CH3OH, means there's lots of it. There is a ton of solvent always. And it's going to come and grab that H. The only thing I need to see in the box is the result. Get my color scheme back here. We have the green for the carbons that used to have a leaving group. I reversed it with my nucleophile turning green. I'm sorry about that. Now it's blue. And if you write that down, you get 1 out of 2 points. Do you know why you get 1 out of 2 and not full 2 points? Because you're not telling me about the stereochemistry. The safest way to show you get a 50-50 mix of R and S without having to do a lot of writing, I don't want you to draw the R molecule and draw the S molecule. You don't have to do that to get the information across to me. You just point to the stereocenter. Please do it this way. Don't use words, and just say 50-50 RS. Some of you want to just write the word racemic there. That's good for this example, but it will fail you if there's other stereocenters present in this molecule and you didn't make enantiomers, you made instead diastereomers. So I gave you a way to do this that works for every example. Just point to the stereocenter where they got the racemization and say half of it's R, half of it's S. And you're done. That's a 2-point box. On the test, it should say 2 points. Most often it's 1, but if the stereochemistry is involved, it's always 2. All right, we're back to this one. And what am I going to do to this one? I'm going to make this one a better example. So I'm going to change that from a methyl to an ethyl. And you'll see in the book that's the next example anyway, or something close to it. And then we're doing something like I just said. There's 2 stereocenters in this molecule, and we'll call this alt. It's an alternate version of problem 4. Why? Because it does at the same time. I need the original to have the same corrections. I was hoping I could do it fast. So I got a stereocenter here in my alt version, and a stereocenter where the leaving group is the chloride. And do the analysis. Don't try to speed ahead to the answer. That is a tertiary carbon. Watch. 1 bond to carbon, 2 bonds to carbon, 3 bonds to carbon. Tertiary has only one conclusion, SN1. Go straight to the answer, but don't stop your analysis. I wrote SN2. Wow. Yeah. I'm doing that a lot. Writing something other than what I said. SN1. Tertiary can't do SN2. Why? The real answer why it can't do SN2 is it became a cation before there was any backside attack even possible. There's an alternate reason that's not as important because the cation happened first. But the alternate reason is the backside's blocked. But the thing became a cation before the nucleophile even could consider coming to the backside. Anyway, I'm just talking. Tertiary, SN1, that's your answer. Nucleophile is cyanide. Strong. You're thinking SN2, but please, you can't change their mind on a tertiary carbocation. They are intractable. Oh, that's a good word, intractable. Tertiary must be SN1. Will not change that. Not today, anyway. Solvent is DMSO. Let's just draw some DMSO because it's a cool structure. Does that structure remind you of anything? DMSO, dimethyl sulfoxide. It reminds me of the end product of ozonolysis because it is. There's much cheaper ways to make DMSO to use as a solvent. Still used a lot in veterinary science as a relaxing agent for animals' muscles. We found it to not be so good for humans. Not that it doesn't work as a relaxing agent, but it brings so many things in from the outside environment because it's such a good solvent. And you can deliver carcinogens through your skin by rubbing DMSO on your skin in an environment where there's carcinogens in the air. So great solvent. Be careful with it. That's all I'm saying. What category is that? It is polar aprotic. Polar without having an H bonded to O or N. That's what that means. Polar without having a hydrogen bonded to oxygen or nitrogen. Polar because it has an S double bond to O, 2.5, 3.5, electronegativity difference of 1. And that favors SN2 as well. Trying to see if I can get people to change the mind of a tertiary carbon to make it SN2, and you can't, so don't. And you're going SN1. And this is where the word racemic would give you a, you'd only get 1 out of 2 in this box. And what are we going to do? I'm just going to draw a cyclohexyl in green. There's no chemistry happening over here. Please do not change this stereo. Oh, that's a CH3. Do not change the stereochemistry over there. But the chemistry does change over here. You've got an old methyl. You've got a new cyanide. Often with the cyanide reactions, I ask you to draw all pi bonds. So I would, just to see if you know what cyanide looks like. So you'll see on a lot of tests, you'll see these commands in tops of boxes. Draw all pi bonds. And get that, and you're going to get 1 out of 2 points for that. You've got a point to that stereo center that's used to be exclusively, what was it? Used to be not R, therefore S. I think we used this color before. And when you're done, it's 50-50 RS. You have to acknowledge that. Why 50-50 RS? Well, you told me SN1. What was the first word that came into your mind when you said SN1? Carbocation. Is there a backside there? No. You're going to get a 50% coming in from a wedge. That'd be in front. 50% from behind. That would be a dash. And that is a good stop for this segment. And we will pick it up with problem number 5, 6, and 7 after the break. And I'll see you then. If I can remember how to stop this.